Okay, so let's study the binary outcome model, in which the outcome is not going to be deterministic anymore. So, there are all kinds of ways to model a random outcome. The easiest way is to say the outcome is binary, which means the outcome follows a Bernoulli distribution with two possibilities. So let's call them 0 and 1. Given the effort, which is A, I'm going to assume that the probability for a good outcome to be observed is P of A. Okay, so P of A, this probability function, is increasing and concave and no greater than 1. So if the agent puts more effort, it's more likely for the outcome or for the project to be successful. But effort has diminishing marginal benefit. Okay, when you already put a lot of efforts, more effort would be not so useful. Okay, so we should still discuss four cases, right? Just like the previous video. The action may be observable or not. The agent may be risk neutral or risk averse. In each case, the principal should design a compensation plan as what we did. Here are a few things. Because the outcome is binary, either 0 or 1, so if we are designing an output-based contract, then that contract would only contain two numbers. What I would pay when the outcome is bad, what I would pay if the outcome is good. Okay, because the outcome is binary. So if this is an output-based contract, then it's W0 and W1. When the action is observable, then we should ideally or we should technically be able to contingent the contract, contingent the payment according to the effort level we observe. Okay, but as you can already feel, this is not needed, because if we can really observe the action, then we're going to assign a value, assign a work level to the agent. Okay, we will decide A, and once we do that, there is no need to specify a function. All we need to do is to specify the value of the payment when the effort is A. Okay, so it doesn't really matter. All we need to do is to work with two numbers, W0 and W1. We know that the shape U, the U function has different shapes. Different shapes can decide the agent's risk attitudes. So that works directly with risk-averse agents. And once we have that, the risk-neutral agent can be studied as a special case with the assumption that U of W is just W. So we will study the more general case, and if you need a special case with risk-neutral agent, just do it. So if the action is observable, the principal's problem would be formulated in this way. What's this? I'm going to decide three numbers, the action level, and the two payments when the outcome is good and when the outcome is bad. With probability P of A, I will see a good outcome. In that case, I'm going to earn $1 because Q is 1. But I need to pay W1 to the agent. With probability 1 minus P of A, the outcome is bad, and then I earn nothing. I earn 0 because Q is 0. But I still need to pay the agent W0. Okay? The agent can earn this amount of money when the outcome is good or when the outcome is bad, but that money goes into the utility function so that the agent gets the expected utility according to the earning, and then the agent need to pay the cost. Okay, so that's the format. The principal need to make sure that the agent can stay in the system by earning a non-negative utility. So the constraint again must be binding at an optimal solution. Okay, but now it's not really helpful because we just don't have something to plug in back to the objective function. So now if we really want to solve this problem, now it's time to use the KKT condition. Okay, we really need it to reduce the program. So let's think about what should we do. Here, we're going to associate a Lagrange multiplier to this constraint, right? And if you go back to the slides that when we were introducing the KKT condition, in that general case, we assumed the constraint is less than or equal to constraint. In that case, your lambda would be non-positive. So here, because we have a greater than or equal to constraint, our lambda should be non-negative. Okay, so that's something we will use in the next slides when we show you the derivation. But here, let me highlight the outcome. Let me highlight the result. If I have an optimal plan that can solve the principal's first best problem, then I would have WE0 equals W1. Okay, I will pay the agent a fixed payment. I will pay the agent a fixed payment. No matter what happens, no matter what's the outcome, the agent will get the same thing. Why is that? Well, the agent is risk averse, while the principal is risk neutral, right? So the agent actually prefers a fixed payment rather than an uncertain payment. So if the expected values are the same, the agent prefers a fixed payment. If the agent prefers that, then giving what he wants would be more profitable to the principal, right? Because then in some sense you don't really need to worry about whether he likes it or not. So the agent hates risk, but the principal does not care about risk. So the best thing is for the principal to take all the risk. So let's see how that can be proved in the next slide. Okay, so given any non-negative lambda, I first find the Lagrangian. So that should be the objective function plus lambda times those things in the constraint. Okay, those things in the constraint. And then I don't need too many steps. All I need to do is the first order condition with respect to W0 with respect to W1. I can see that if I differentiate the Lagrangian with respect to W0, I can get this, or with respect to W1, I can get this. Now, this is just very basic differentiation, so let me just leave the outcome to you. Please verify them by yourself. And once you do some simplification, you get this. Your optimal W0 and W1 and the given lambda should satisfy the two equalities, okay, according to your first order condition. If W0 and W1 is optimal, then this must be satisfied. And that directly means W0 and W1 must be identical, right? Must be identical. You probably want to do one final check, is that W prime is positive. So this makes sense because the given lambda would also be non-negative, or in the sense that it's really positive. Okay, so this equation can really be satisfied, and to satisfy them, we really need W0 to be equal to W1. If I want W0 and W1 to be optimal, this must be satisfied with no exception. Okay, so again, what's the intuition? I can control the effort, so I will decide what the agent should do. That's fine. And I want to compensate the agent, the cost, for doing that action. And what's the most efficient way to do that? Is to give the agent a fixed payment, because the agent simply hates risk. So all I need to do is to ask him to do something and pay him the cost. Very quickly, we're going to see that's not going to work if we are working with a risk-averse agent, and when the outcome is not, and when the input is not observable. So suppose the action is unobservable. Okay, now I cannot ask the agent to do something. I can only offer W1 and W0 and then for the agent to choose A to maximize his own expected utility. Now, A is a variable in this objective function. So an optimal A would satisfy the first order condition. Okay, so I differentiate this with respect to A. This goes to P prime of A, P prime of A, U plus minus and 1. So this is the first order condition with respect to A. The principal's problem would be this. Again, this is the IC constraint. This is the IR constraint. All I need to do is to say, okay, I cannot control A directly, but I know given W1 and W0, A would be chosen so that the first order condition of the agent's problem would be satisfied. Then this is the principal's problem. I cannot control A directly, so I design my compensation plan W0 and W1 to induce an effort level. To solve this problem, in the next slide, we will show you how to use the KKT condition to solve that again. But the most interesting thing that we want to highlight is if there is an optimal solution, it's going to satisfy W1 is greater than, strictly greater than W2. Why is that? Now, the agent does not like to work, right? The agent has no reason to work if the agent gets a fixed payment. If I give W1 equals W0, okay, think about the case that you are an agent. You get a fixed fee, no matter what's the outcome. Then there is really no reason for you to take any action. Okay, so now, because of the hidden action, the principal really need to offer something, offer a difference of W1 and W0 so that I can get some positive action. So I really need a bonus for a good outcome. A bonus for a good outcome. Okay, so that's proof that previous argument. So now we have two constraints, right? So I need two Lagrange multipliers. And technically, when you have an equality constraint, your Lagrange multiplier would be unrestricted in sign. Okay? If it's an inequality, then you have a sign constraint. But when it's an inequality, your mu for the second constraint would be free. Can be positive, negative, or 0. Okay, so given Lagrange multipliers, the Lagrangian would be this one. The objective function, lambda times the first constraint plus mu times the second constraint. First order condition would directly give us blah 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 and blah blah blah. No. All you need to do is to do this calculation once so that you can verify that they are the same. But basically, it's just a first order derivative with respect to W0 and W1. So please try to verify these two equations and tell me if they are wrong. Okay, but after that, we can do further simplification. That simplification is to make the conditions presented in this way. Okay, it's very interesting because once you do this, you can make a direct comparison between these optimal conditions with the optimal conditions for the first best scenario. So first of all, if we observe this, if we look at these conditions, if mu is 0, then this term goes away, this term goes away. The remaining thing is just the first best optimal condition. Okay? And we would set W0 to be W1. So that means the principal has the option of implement the first best outcome. Okay? If that's really what he wants. But actually it is not, because the principal now has the chance to alter mu to improve her expected profit. Okay? The principal can set mu to be, the optimal mu for the principal to maximize his own expected profit may actually be positive or negative. Okay? No one says it must be 0. So actually we can show that the optimal contract satisfies mu greater than 0. Okay? When mu is greater than 0, the principal can really do the best. Okay? Can really do the best. If you have some free time, try to think about why mu must be positive for this to be an optimal solution. But when you take that as given, let's think about what's going to happen to mu at W1 and W0. We know that U prime is decreasing because U is a function like this, right? So your U prime is the slopes. The slope would be decreasing. And given that, we know U prime, 1 over U prime would be increasing in W, okay? So this is an increasing function. So that means if your right-hand side is larger, then the W would be larger. Then immediately, if we know mu is positive, then all the terms here are all positive numbers, right? So that means for this term, okay, it is lambda minus a positive thing. For this term is lambda plus a positive thing. So this is going to be greater than that. So your W1 would be greater than W0. Done. Okay? So with the optimal conditions, we can prove that W1 must be greater than W0 as long as mu is positive in an optimal solution. And it can really be shown that mu would be positive in an optimal solution. Then that's the end of the proof. So quick summaries. When the agent is risk-averse and the outcome is random, then whether the effort is observable really makes a difference. When the effort is observable, then we don't really have the moral hazard problem. All we need to do is to set the two payments to be the same, to remove risks from the agent. That's the most important thing to do in this scenario, okay? Because the agent does not like risk, so that's the principle. Take all the risk. Then the system would be efficient, and the principal can earn the most amount of money. But if the effort is unobservable, then now the one more important thing to do is to provide some incentives for the agent to work. Then we really need to set W1 to be greater than W0. Otherwise, the agent really have no reason to work, and then we would have no probability for the outcome to be successful. So here we can see information asymmetry or hidden actions actually results in a deviation or a distortion on the optimal contract, okay, and results in efficiency loss, which is the central theme of this course, right? Information asymmetry now really creates a problem. It can be shown that if the agent becomes risk neutral, okay, then the second best contract would also be efficient. So that means here, the derivation we did is that the agent is risk averse, and we show you that whether the effort is observable will give us a different contract. But if the agent is risk neutral, we can prove that the two scenarios will give you the single outcome, the same outcome. So that's something that I don't want to show in the videos directly, but it can be done. So we can collectively we can say that risk aversion is really necessary for moral hazard problem. Okay? In this video, we are talking about a scenario with a random outcome. And then we say that either we need unobservability or we need risk aversion. If the agent is risk neutral or if the effort is observable, then we don't really have moral hazard problem. Okay? So yeah, think about it. Thank you.